In this video, we'll explore how projectile motion works when an object is launched from a height and lands at a different level. Get ready for a real-world rescue mission involving math in action. A rescue team stands on a 70-meter high cliff and needs to deliver supplies to hikers stranded at the base of the cliff. They launch the package at 30 meters per second, at an angle of 35 degrees to the horizontal. What is the maximum height reached by the package? How long will it take for the package to hit the ground? How far from the base of the cliff will the package land? What is the velocity of the package just before it hits the ground? Let's label the point from which the package was launched A. The maximum point reached by the package will be labeled as B, and the point at the bottom where the package landed will be called C. To calculate the maximum height, we'll use the formula that we derived in the first video of this playlist. The link is in the description. Replace U with the initial velocity of 30 meters per second. Replace theta with 35 degrees, and we are using 9.81 for G. So the maximum height is 15.1 meters vertically from the launch point A, located at the top of the cliff. The height of the cliff is 70 meters. This means that from the bottom of the cliff, the maximum height reached by the package is 15.1 plus 70. That's 85.1 meters. To find the total time that the package takes to reach the ground, we'll analyze the motion over two separate sections. The motion from point A to point B and the motion from point B to point C. In video 1 of this playlist, we derived the formula for time taken to reach the highest point B from the launch point A. That's U sine theta over G. Replace the initial velocity U with 30. Theta is 35. G equals 9.81. This gives T equals 1.75. So the time taken for the package to travel from point A to point B is 1.75 seconds. Now let's calculate the time taken to travel from point B to point C using the third kinematics formula. We are taking only the vertical component of the motion since we are analyzing the fall from the maximum height to the bottom of the cliff. Now let's find the time, T. At the maximum height, the package will pause momentarily, so its initial velocity, U, is 0. So we are left with S equal half A T square. Multiply both sides by 2 to get rid of the fraction. Now divide both sides by A, then take the square root of both sides to get T equal the square root of 2S over A. The vertical displacement from B to the ground is 85.1 meters, so S is 85.1, and as usual, G is 9.81. Hence, T equals 4.17. So the time taken from B to C is 4.17 seconds. So the total time taken for the package to reach ground is 1.75 plus 4.17 equals 5.92 seconds. To answer part C, we need to find the horizontal distance from point A to point C. Recall that displacement equal velocity times time. The horizontal component of the velocity is always U times cosine theta. The value of U is 30, theta is 35, and we just found the total time taken from point A to point C to be 5.92 seconds. So the range R is equal to 145.5 meters. To find the velocity with which the package hits the ground, we need to find the final vertical component and the final horizontal component of the velocity. We can use the first kinematics formula to analyze the motion from point B to C vertically to find the final vertical component. At the point B, the object paused momentarily, so the initial velocity u is 0. The acceleration a is due to gravity, so a equals 9.81 and t is 4.17, since we found earlier that it took 4.17 seconds to go from B to C. So the vertical component of the final velocity is 40.9 meters per second. Let's call it v with a subscript y. The horizontal component of the velocity is always u times cosine theta. This value remains constant throughout the entire motion since it is not affected by gravity in the same way that the vertical component is affected. So the horizontal component of the velocity is 24.6 meters per second. To get the velocity with which the package hits the ground, we can use Pythagoras' theorem since it will represent the hypotenuse of the right-angle triangle shown here. Hence, we get V equals 47.7. We can call the angle of impact theta. Using the trig ratio tan theta equal to opposite over adjacent, theta is tan inverse Vy over Vx, which is 59 degrees. Hence, the package hits the ground with a velocity of 47.7 meters per second at an angle of 59 degrees. By applying physics and math, the rescue team safely delivers the package. Understanding projectile motion helps in real-life situations, from rescue operations to engineering and sports. This is Math in Motion. See you soon when we'll be looking at another type of projectile motion. Remember to like, share, and subscribe so that you can be notified.